This is the Physical Activity Researcher Podcast, a podcast for researchers of sedentary behavior, physical activity, and sports. Join for a relaxed dialogue about research design, practicalities, and, well, anything related to research. Learn from your fellow researchers useful and relevant information that does not fit into formal content and limited space of scientific publications. And here is your host, researcher and entrepreneur, Olli Tikkanen.
Welcome to Physical Activity Researcher Podcast. And today we have a guest, Timo Rantalainen, Doctor of Sports Sciences, who currently works at Gerontology Research Center in University of Jyväskylä. And Timo is doing research in bone, muscle interactions, and physical activity assessed with wearable sensors. Really nice to have you here, Timo. Thank you.
Thanks for having me, Olli. It's my pleasure.
Yeah, and I have known you for quite a long time, from the student times already, and I remember always that you like the mathematics and algorithms. What is your interest? Are you making algorithms now, or what do you do on a daily basis?
Well, that's precisely what I do. I'm a racing nerd. Pretty much all I do is bang away on my keyboard.
Yeah. So I heard you got the funding right now. What kind of funding did you receive?
Right. So this is actually really big news to me. I got funding from the Academy of Finland, which is the biggest funding source we have here in Finland, and I got a academic fellowship, which is the best kind of grant you can get. So it's a salary for myself for 5 years, and then I get to recruit a PhD candidate and a postdoc pretty much for the 5 years. So it's really an excellent source of funding.
Yeah, congratulations.
Yes.
Yeah, I know that researchers, they keep applying and actually failing most of the time, especially in certain fields and certain countries where the funding there's not that much funding. So I can really feel that you're happy, and this is a big thing for your career.
Absolutely. I'd actually go as far as say funding is scarce anywhere you go. Competition is very hard. So I've only worked in Finland and Australia, but in both of these countries, your success rate is anywhere between 7 to 20%. So 1 in 5, and that's at the high end. So it's difficult to get funded wherever you go. In my case, it took 9 years to land this big funding since I graduated. So it's a rare treat.
Yeah. So you like mathematics. So if it's 5%, is it just that you apply 20 times and you guaranteed succeed?
Yeah, I'm not entirely sure that's the way probabilities work. But it's not far off though. So I would say that I have popped in at least 30 applications over my career, and I've landed, I think, maybe 6 or 7. Some of them small, but nevertheless.
Yeah. So it might work. You just need to apply, and somebody likes your idea.
That's precisely what it is. Someone needs to get excited about the idea proposed, and unfortunately, there is an element of luck in the process. So that's been shown in studies as well. When we studied who are the people who get funded versus those who did not get funded, and we look at their research output, how many times they're cited, all of those, you can't really tell them apart.
All right.
But so we're in a good position in that sense. So we got a sufficient number of highly qualified people who know how to do research, and therefore we don't have enough funds to support all of them.
So you need to have some new idea at least to get the funding. So what is your research about, the new project?
So as you might expect in this particular podcast, I work in looking at physical activity. And so what I asked funding for was to explore the idea that instead of looking at whether physical activity is good for your health, we kind of turn the tables a little bit, and I'm asking the question of, can we tell something about your physical state by looking at how active you are in your daily life? And the idea is, so it stems from very basic research on roundworms, and this was published somewhere in the very early 2000s, where they looked at the motility of roundworms. And they found out, and so this is a very interesting species because they're genetically identical, all of them. So therefore it's not genetics that determines their longevity. But nevertheless, there's massive variation in how long they live. And so what was shown was that the motility of these roundworms predicts if they're going to die or not. So the roundworms that were still active, let's say 30 days after they were born, they were going to remain to be alive. But if they didn't really move around at all, they were going to die off quite soon. So this is that's kind of the framework I wanted to, or I took in this application. So I'm asking whether in humans the same is true. So if you are active today, are you then likely to be alive, let's say 2 years down the track? Of course, I'm not going to be able to answer that question during my project, but nevertheless, that's kind of the framework I went with. And I guess I should have started with that I'm working with older individuals. So this is in gerontological research.
Yeah.
And so that's the framework I'm currently working.
Yeah. And how old do you plan to have your participants?
So I've got 3 groups. So this is actually a part of a larger grant. The professor I'm working with at the moment, Timo Rantalainen, got from the European Research Council. And so we've actually completed the baseline measurements just at the end of last year, where we had a group of 75-year-olds, 80-year-olds, and 85-year-olds. And their population representatives, so they were randomly, so we had the population register, and we ran them up, and whoever signed up for our study, they're in our study, and therefore their population representative.
Yeah, and do you plan to follow them for more years, or do you just do it cross-sectional, or how do you plan to do your study?
Right, so and so that's what I got the funding for, is the follow-up. So we got the baseline data finished at the end of last year. Right, and I asked funding for 4-year follow-up. So we're going to, whoever had, so first of all, the whole population we have sampled to date is 1,000 people. But out of those 1,000 people, 493, I think, or something akin to that, signed up to wear accelerometers on them for 7 days. And so we had 2 concurrently worn accelerometers, one on the thigh and another on the thorax. And so those 493 we ring up in 4 years' time and ask them to come back for repeating or replicating the measurements we did just last year.
All right, that's very interesting. So I lost my train of thought. So it's quite easy to see that if somebody's in really bad health and they are bedridden, they don't move much, and there's much higher likeliness that they will die or not survive. So do you think it will go all the way to the continuum of physical activity, that the ones who are really active, they still have like much more life left than the others who are moving a little bit less, or what do you predict will be the...
Well, that's a really good question, and that's I don't think we know the answer to that at this stage, but that's actually kind of what's driving me in this physical activity research. Why do I find it interesting is for a whole range of different medical conditions like type 2 diabetes, Alzheimer's, or mild cognitive decline, heart disease, really most of our chronic conditions. If we knew that someone's going to develop a chronic condition 2 years ahead of time, we would actually be able to prolong or delay the onset of the medical condition by maybe a year, half a year, anywhere between half a year to maybe even up to 2 years. It's particularly with type 2 diabetes, we got pretty strong evidence that by being physically active, by monitoring your diet, you will be able to postpone the onset of the disease proper. And that's why I'm interested in physical activity as a marker. So what we have at the moment is we are unable to predict who is going to develop preclinical conditions from a healthy state. So that's something we cannot do with any degree of certainty. But perhaps there are some early changes in your behavior, some early changes in it could be your metabolism, it could be anything really. So what I'm interested in is because of my background in sports, and that's the thing I can do, is I can look physical activity using accelerometers. So that's what I'm concentrating on. But what I'm hoping is that there's something in your behavior, maybe it's something in your gait, maybe your gait becomes more complex, and we can return back to that later on why that might be a marker. But if there is some sort of indicator that you are heading into trouble today, if we then target you and intervene with your behavior, your diet, your sleeping patterns, whatever it is, and we're able to postpone the onset of the clinical condition by even half a year, that's a half a year of happy life you would not have without this capability. And so that's kind of why I find it a worthy topic to spend my time on.
No, it sounds very, very relevant. So do you think there's what variables will be the predictors? Do you think it will be the light activity, moderate, vigorous activity, or do you think it will be a pattern of walking that it's maybe not symmetric, or what do you think will be the predictors, the best predictors of health?
Well, that's a really, really good question. Again, one I don't have an answer to.
Yeah.
So I guess the tradition of physical activity research has been a questionnaire. You've been asked whether you do physical exercise or not. And so that's where we started from. Then someone realized that we can actually use accelerometers to start getting the same or answering the same question with objectively measured data. So it doesn't depend on the individual doing the measurement. And then I'd say maybe the last 10, 15 years, we've realized that there may be, or there's more to it. So we need to look at the patterning of physical activity. To me, a good example of why patterning might have an effect, it comes down to physiology. So what we know of bed rest or immobility is that you only need a very short time of inactivity, and you start losing your muscle, you start losing your ability to drive the muscle with your brain, you start losing your connective tissues, you start losing your bones. So even just a 1 week period of complete bed rest, and we're starting to see this loss of function. So then you'd go back to looking at the way people accumulate their physical activity. Maybe you're a weekend warrior, so you go jogging on a Saturday, and then maybe you go pedaling on your bike on a Sunday. And then the rest of the week, you work in the office, you don't really do anything for 5 days. Is this going to be beneficial to your health? What happens if you change your habits and you actually, instead of doing 2 big bouts of exercise, you did a little bit of exercise every single day? So the total amount of minutes accumulated in a week would be exactly the same. But would it be the same physiologically, or would it be the same for your health? I think there's a good reason to believe that physiologically, if you got very long periods or multiple days of inactivity, that's going to start to affect your physiological state negatively compared to breaking it up with a bout of exercise intermittently.
Yeah, I think clearly physiologically it's not the same. The question is whether the effects are kind of close, how close they are.
Right.
Of course it's different. It's different stimulus. If you go for a short run today, tomorrow versus in the weekend, of course it's different. But how different is it, and how different is the effect? And I remember reading something about rehabilitation research that they had, like, I think it was maybe patients with the ACL reconstruction or maybe osteoarthritis, I don't remember, but then they were looking like their physical activity, and the ones who were doing fine and the ones who were not doing that well, the physical activity was the same. But when they actually looked more closely, they could see that the bouts under 10 seconds and then the very long walking bouts were totally different. So basically, the ones who were not doing well, they were avoiding like really short walks. Maybe they had some pain when they started, and then the pain got back when they were continuing for a longer time. So there was clear that when you start to look the data just more closely, you can actually find quite interesting markers. Even on average, everything looked the same. So I think it could be same with this that when you just look closely enough, there's something interesting in the data.
Right. Well, I think that's a really good example of sort of a chance finding. I'm not sure that you'd necessarily hypothesize that this is going to be the case when you start your study. And that's why we have to do these cross-sectional studies where we just explore. So what do we see in the population at large? So some of that work has been done, but to me there's a lot more that we need to do, even in the cross-sectional space of just looking at what's the state of people living in the community right at this moment before we can really start kind of identifying the things that make a difference, like you said. So being able to identify someone who has a good prognosis on their ACL tear after it's been repaired versus someone who doesn't have a good prognosis, this will make a big difference for the individual. So we know that, particularly for the ACL, let's use that example. So it is very common that you develop a knee osteoarthritis in the long term. This may be driven by changed mechanical load. And if we can identify it early on, we can then intervene and potentially prevent that osteoarthritis from developing.
Yeah, and I could imagine that some disease conditions you can maybe see something in the acceleration. You can detect really closely how the leg actually moves, whether there's some sort of shaking or something. So I think you could even detect some disease conditions when you just find the correct variables to look from the data. Or what do you think?
Right. I'll actually take this segue back to what I was talking about when I mentioned the complexity of gait. So a completely different variable we're looking at. But I like this particular example because there's pretty good evidence to show that this actually works. And so this is for cognitive impairment, for mild cognitive impairment. Now there's kind of two parts to it. So first of all, walking is to an extent automated in humans. Certainly it's pretty much fully automated in cats. So if you take a cat and cut their spinal cord, you can still make the cat walk. So you know that there's no volitional control required. Humans have the same networks. They're not as strong, but nevertheless we have the networks. So walking is considered an activity where we need a little bit of volitional control, but it's relatively easy. So we can then undertake another task, let's say counting backwards or talking to a mate while walking. And so what was discovered, and I thought this was a really interesting way of finding out something that's really kind of, when you look back to it, it's obvious that that's the way it works. But what happened was geriatrics, so people or medical professionals who work with older individuals, found out that one of the more effective ways of detecting early Alzheimer's is by walking with someone and asking them a question. And if they stop, then that's when you're concerned. And so it comes down to this idea that we have a single processor, our brain, and if part of that processor is being used to walk you, then if you add the load by adding a second task, it's called the dual task paradigm, then your walking may become disturbed. And if your capacity is diminished to an extent where you can't undertake the second task, which is talking in this case, then you have to stop, otherwise you'll fall over.
And do you think it's about the capacity of the brain or the fact that you need to do the walking? It's not automatic and you need to do the walking, and then when somebody asks you a question, you don't have any more free capacity in the brain. So do you think it's because you really need to actively be walking and thinking of walking, or that your capacity in the brain is diminished?
I think it's kind of both.
All right.
But the fact that we do have to have volitional control over our walking, it enables us to use this technique. Because otherwise, if we didn't have any cognitive load from walking, then it shouldn't be affected by asking a question. I guess now circling back to the variables we were interested in. So what happened with this was this phenomenon was found, and then people were doing gait analysis. And with gait analysis, you can look at the mean step length, mean step velocity, and so forth. But you can also look at the variability of gait. So if I take a stride that is 1.5 meters long now, and then my next step is 1.4 meters. Now there has been a variability in my stride length. And we can quantify how much of the variability we have. And turns out that healthy people have less variability in their gait than those who have mild cognitive impairment, or those who have Parkinson's, or those who. So there's many clinical conditions that affect gait variability, but the cognitive impairment is one of them.
Yeah.
And now, when we add that second task of walking and then talking at the same time, or counting backwards is what's quite often used, turns out that the increase in variability is higher in those who have cognitive impairment or have Alzheimer's.
Mm.
And I'm actually currently testing whether we can go further back to a more preclinical state of cognitive decline, which isn't yet cognitive impairment, and can we detect the difference between those who are completely normal, don't have any complaints about their memory, to those who complain or are worried about their memory. Maybe that someone's, or maybe they realize that they started forgetting things.
Yeah.
And so that's now gait variability is interesting for that reason. There's other reasons as well, but that's one of the reasons why gait variability is interesting. It may be a preclinical marker of impending cognitive impairment. And again, for cognitive function, we know that if we do cognitive training, it will delay the onset of cognitive impairment. So that's, and again, that's circling back to what I was saying about why I think this is meaningful. That's one of the reasons. So we have some evidence for particular clinical conditions that we can actually postpone the clinical onset if we know about them beforehand.
Okay, let's get back to that in a moment and hear a few words from our sponsors.
This podcast is sponsored by Fibion, a research device that has been shown to be valid in tracking sitting, standing, physical activity and energy expenditure. Furthermore, Fibion has been shown to be valid categorizing physical activity into light, moderate and vigorous intensity. Get scientific validation and learn more about Fibion at fibion.com/research. The Physical Activity Researcher podcast has created an activity tracker purchase guide for researchers. Get your free copy from the link in the podcast description.
Yeah, and it's really interesting the thought about that. It's kind of the same energy that we are using for example, walking and thinking. And I've been testing it after I read about it. I was testing like that. If you're running up the hill and you push yourself quite hard, it starts to get impossible to think anything else. And then you slow down, then you can think something simple. And then when you slow down for a walk, then you can start thinking more. And then when you speed up again, it's like there's just no space for thinking.
That's an interesting concept. I don't think it's been talked about in those terms, but I think that's an interesting concept of you have to actually consciously be, or volitionally be pushing yourself when you're working hard.
No, I've been testing it myself quite a bit, and I'm pretty sure it works like that. You should try it going uphill. And then I've been thinking also the same, that when you actually cycling on an ergometer, it's like if I don't concentrate all the time that keep going, I kind of slow down really a lot, which doesn't happen as much in the running. So I think maybe we are more designed for running, like my legs know how to run better than cycle, because for especially ergometer cycling, I really need to all the time think that keep cycling. If I just get drawn to my thoughts, I almost stop.
Right.
Yeah, so I don't know if this is also related to that, but you should test this by yourself. I think it's really
that's an interesting thought. I mentioned the dual task paradigm. That's kind of a keyword for what we use in gait analysis. But that's a really interesting thought. So first of all, we don't have a reflex circuitry for pedaling, because that's not the way we do locomotion. We do walking and running, and we have reflex circuitries for those. So that could, I think it's a really interesting idea. But then, so what happened if we did dual task pedaling? I'm not entirely sure if that's been tested or not.
Yeah, maybe you have a new idea for your research, that actually if you take some tasks which we are not designed as much, that how does it affect the dual task? Yeah.
Well, the good thing about bicycle ergometer is we can track the pedal cranks with very high degree of accuracy. So that this is a big challenge in gait analysis. It's a complex phenomenon, and what we can do is, or we're limited by the fact that it's so complex. So we could be measuring joint angles, we could be looking at the distance from heel strike to the next heel strike. There's just a really large number of different variables we could be looking at, which is an issue, because then it becomes difficult to decide what we actually look at. But if you go looking at the crank velocity, crank angular velocity, now this becomes much more simple because it's just one variable we're looking at, and we can start plotting the previous stroke to the next stroke and so forth, and kind of make it simpler.
Yeah, that's true. There's no balance component or any other which would distract. So now you have the accelerometers on the thigh and thorax, right?
Yep.
Yeah, and do you actually analyze them like together, that you kind of look interaction? Basically, the other one is looking the movement of the body mass, and the other one is looking the acceleration of the leg. So do you plan to analyze them together, or are they analyzed independently?
Well, they could be analyzed either way, and we will of course do this. So I guess we'll take one step back. So what we typically take from accelerometry is the counts, and we divide them into categories of sedentary behavior, light activity, medium, and vigorous activity, or moderate and vigorous. Sorry. And so that's of course something we can do from thorax. We can do it from the thigh. There isn't an equation for the thigh that you can find from the literature. So we calibrated it on the treadmill. So we asked people to walk at different velocities, and then just fitted a linear fit onto it, and then coupled that with their oxygen consumption that we measured as well, and decided on the thresholds for these different categories. So that's one thing we are going to do. We are going to take a look at the minutes, how are they accumulated. But the other thing we're really interested in, and this is why you actually would like to have two accelerometers on the individual, is posture. So when we now use these concurrent records, we can take a look at whether the thigh was horizontal or if it was upright. So of course, if it's horizontal, you're either lying down or sitting. And if it's upright, you're standing up. So you might be walking, you might be running, whatever, but at least you're upright. And the same is true for thorax. So from thorax, you can figure out whether you're lying down versus sitting or standing. So with either one of these sensors in isolation, you cannot tell apart lying down and sitting, or sitting and standing. But when you combine these two sensors, now we are able to, with high confidence, say that they were either lying down, sitting, or standing up. And then the standing up time we can then further divide into just standing around and then walking, and that's going to be based on the amount of acceleration we see. So if there's very little acceleration, they're standing in one place, and the more acceleration we observe during upright, the more vigorous activity they are undertaking.
And you said that you did a protocol on the treadmill. So did you do like individual calibration for all of them with the?
That's a really good question. No, we did not make an individual calibration. So and that's the norm is not an individualized calibration for physical activity. The way you find, so there's multiple ways of figuring out how vigorous physical activity you're undertaking. So first of all, the underlying idea is all based on energy consumption. So if we just lying down, that requires 1 MET, so one multiple of your basal metabolic rate. Standing up is about 1.5, and then you go to walking and running, whatnot. And this is how we define sedentary behavior. So sedentary behavior is anything less than 1.5 multiples of your metabolic rate while at rest. 3 METs is the threshold for moderate, and 6 METs is the threshold for vigorous physical activity. And now what we've done is we've had an accelerometer typically on the waist. In our case, it was on the thorax or on the thigh. And we need to figure out how many times your metabolic rate are you consuming at this time in order to categorize a particular minute.
Yeah.
Which is a tall order.
Yeah.
And of course, it's very easy to see how you go entirely wrong. So we've got a accelerometer on the thorax, and we're pedaling a bicycle. There's very little accelerations on the thorax, but you're actually consuming a lot of energy. So this is a massive issue to begin with, even if it was individualized. But then going back to the way we actually go about this business is we recruit a population and we ask them to undertake a battery of different activities, and we simultaneously measure their energy consumption. The battery of different activities that are undertaken varies from study to study, but very typically it is only going to be walking on a treadmill, which of course is not reflective of the way what we actually do in the room. But it's by necessity. We just don't have. Of course, we could record just a full day of physical activity concurrently with oxygen consumption and the accelerometer in place, and then do some sort of a fit. So is it now going to be a linear fit? Is it going to be a non-linear fit? All these questions are questions that we don't have correct or incorrect answers for.
Yeah, it's a little bit demanding protocol to wear the mask full day because eating gets a little bit difficult with the mask on. We did actually 12 hours. I also wore the mask for 12 hours. It's just like you took it off for a moment and stick in the food and put the mask back on. So it's not.
But even with that, so it's not individualized. It's never going to be individualized for hundreds of people. Even if you had all of these massive data sets in the background, you still find that the individual values, individual fits of the data are not the same. They're definitely not the same between individuals. And so that's a major caveat in physical activity research in the first place, which is one of the reasons why we're interested in post-track. So we can now start supplementing the acceleration counts or how much acceleration there was over a particular period of time, and couple that with the post-track. And that can kind of refine our estimate of the energy being consumed. Another reason is I'm working with older individuals, and it's been realized over the last, let's say, 10 years, that older individuals, of course we always knew that older individuals are less vigorous in their activities. They walk slower, they do a lot less running than younger individuals. But we kind of realized that this actually has indications on whether we consider a particular amount of activity as measured by an accelerometer beneficial for their health or not. So they may be incapable of producing those accelerations that correspond to vigorous physical activity as defined in young adult population in 6 months. But nevertheless, they may be driving their body in a way that actually goes all the way to their maximum capacity. And that's really all you need. Physiologically, what you need in order to start triggering adaptations is that you actually utilize the energy cycles of the cell. So and this is fundamentally issue in physical activity research is what we measure is accelerations, but it tells you nothing about how hard the person is, subjectively speaking, working. So whether they're close to their maximum capacity or if this is just a walking path.
Yeah. So basically for older people, it might be that their maximum capacity doesn't reach the vigorous intensity activity.
Precisely.
Yeah. So that makes a big difference. So you would need some kind of individual determination of what is their maximum. Like for a top athlete, vigorous intensity activities is not much. They can actually do it for a long time. Some of probably the best trail runners can do it for 24 hours.
Precisely.
And then some
at ease as well.
At ease, yeah. I actually saw the Julian Jornet's video. He did like a record run of 50 mountaintops or something in 11 hours or something, and I saw a video of it, and I was like, wow. But then they showed like after the run, he went there and he couldn't eat even a banana.
Oh, right.
Like he almost like he couldn't just get like one small slice of banana in, and I was like, yeah, even he feels horrible after. So I felt a little bit good like that.
But that's pretty extreme.
Yeah. But it looked like so easy to run 11 hours up and down the mountains for him.
Yeah.
But it seemed that he got tired. So in the end, or afterwards at least. Yeah. So yeah, it's very interesting that it's different for the older people, that maybe they don't reach vigorous intensity activity at all. How do you think this will affect your analysis of the data? How do you plan to have any tricks, develop anything new for this, that it would kind of be more better suited for the older individuals? Do you need to divide it with the more categories than light, moderate, and vigorous, or do you have any plans for this?
Well, that's one of the things we will do, is instead of using just 4 categories, it's a histogram. So histogram is where we take an array of numbers, and we take a look at, let's say the number is 10. We then categorize it into one of the, I call it bins, in my histogram. So we've got a bin from 0 to 5, from 5 to 10, from 10 to 15. So this number 10 would go into the bin from 5 to 10. And so that's what we do at the moment with those 4 activity categories, or one of them being non-activity for sedentary. So instead of doing that, we just take what I'll actually do is I'll divide the spectrum of accelerations from 0 to 2.5 Gs, but you can, in reality, in all the others, the maximum value you will see is 0.7, but that's besides the point. I'll take the range from 0 to 2.5 and divide that into equal bins in 100 portions. And the number could be anything. I find that 100 is sufficient, so you're already starting to see a nuanced view of what actually went on during the day with 100 bins. So that's one of the things we would do. The other one is, I'm not actually, again, going back to the idea of motility or mobility being an indicator of your kind of vigor, or your how much you've got left in the tank. So it may be that it suffices to look at the absolute accelerations, and if you're incapable of producing absolute accelerations, that might be a marker that you're not going to be able to live a life that's still of high quality. So that's one kind of viewpoint to it. And then we already briefly touched on the posture. So one of the things we can do is, let's forget about the intensity of the activity. Let's just take a look at whether you're lying down, whether you're sitting, whether you're standing, or whether you're walking or being more active. And so that's again, physiologically, the fact that you're walking may start triggering some positive adaptation. So it doesn't matter if you're walking vigorously or not. It suffices that you're walking. But not entirely sure if this is the case. And walking is it's really, from a scientific point of view, it's an activity that we are really interested in for many reasons. First of all, it's the primary way of us getting around. Unless you're wheelchair bound, that's the way you get into your car, that's the way you go to the kitchen to have some food and whatnot. So that's our kind of fundamental way of locomotion, is walking. And the hope has been, I guess, is that we could use walking as a way to standardize this method. So instead of using the same category thresholds, huddles, for different individuals, we could perhaps use walking and standardize our physical activity to walking. So how many minutes do you do that's more vigorous than you're walking, and how many minutes are you less vigorous? For example, that could be one way of looking at it. Or let's say in multiples of your preferred walking pace activity. And so that's something we've been really interested in. One of our professors, Fibion Inc, who I also work with, she's been really interested in the topic, and she's now made some headway in this space with Eero. Actually, you know Eero as well. And so what Eero found in young kids is that it's not actually reflective of your physical capabilities. So it turns out that your preferred walking pace may actually be a personal preference. So it may be a poor choice for standardization, which is it's kind of sad news for us. We were all up and about, and I thought now we solved the issue of subjective and objective kind of physical activity. So subjective meaning that we are relating your physical activity to your capability, and therefore we then start using your physical activity to start making guesses on to whether it's going to cause a positive or a negative physiological adaptation. But it's now starting to look that that's not the case. but of course the issue is not settled. This is very early. We haven't even published this yet.
Yeah. I think we tried the same when we were doing studies with the EMG muscle activity, that you usually normalize it for the maximum voluntary contraction. But then we looked at, could we actually normalize it to standing or standing on one leg? But there was too much variability, because you can actually stand in many different ways.
Yeah.
Even though outside it looks the same, you might be using more your quadriceps, your hamstrings. So that didn't really work. And then we were thinking that, all right, maybe a squat, but there's even more variability. It's actually, people do it so different ways, and difficulty of getting what is the knee angle. It depends also on the angle of the ankle.
Yeah.
Like, so it didn't really work. We stick with the MDC, but maybe hopefully you will have better luck with. I think it's a good idea to kind of also have more subjective objective. I don't know if that's a word. Like,
I guess individualized. I think is the
individualized, or kind of personal, more calibration. Yeah, that's something really interesting to look at. And another thing, I was thinking that you have an accelerometer on the thorax. Could you actually look like balance from there?
Well, I haven't personally used it for balance, and I don't think I will either. But I've seen some work being done, and they are sufficiently sensitive to detect the sway. So potentially, yes.
Yeah.
The reason I haven't spent any effort on it is I'm not a big fan of static posturography, which is this. So what you're describing is called static posturography. But what it means is you're standing still and we're measuring how much you sway. And it has some predictive power. So if there are some studies showing that those with more sway are more prone to fall over. But to me it's a poor way of predicting how prone you are to have a fall.
Yeah. I remember in one project we were measuring young and old people balance, and basically the result was that the older had the better balance.
Yeah, well
basically the thing was that they were taking the task more seriously, and they were actually concentrating, while the young were just standing on a plane and thinking something else.
Right, and that's one of my issues with the test. Exactly, it has a U-shaped curve. So young individuals, and then the idea is exactly like that. We don't have to worry about falling over when we're standing upright as young individuals. But an older individual, let's say you've got some problems with your balance, so your vestibular organ is sending you the incorrect signal. You are now actually concerned about falling over. Maybe you've got vertigo, whatever. And so that's one of the reasons why I don't like it. Having said that, there are a lot of variables I personally use and other people use as well that have this U-shaped or J-shaped curve, where an increased value might actually not be a bad thing or a good thing. I think one of the examples we've been grappling with just recently is on heart rate variability. So in young adults, the higher variability you've got in your heart rate, the better it's considered. You're in better condition. But we are measuring, with the device on the thorax, it also measures one lead electrocardiogram. And so we have heart rate variability out of that as well. And what we found is there are a lot of individuals with arrhythmias, and arrhythmia is going to throw your heart rate variability to a very high level, which is of course not indicative of good health.
Yeah, naturally so. Yeah, and you said that about static balance. Have you thought of looking I don't know if you call it balance of walking or the sway of the movement of the body?
Yep, not in those terms, but yes, the idea is the same. So and this is one of the things I proposed in the funding application that just got approved. And there's a little bit of evidence to this. So I already mentioned the dual task paradigm and looking at gait variability and how that's predictive of cognitive impairment. So it turns out that if you ask people to wear an accelerometer for 7 days, and then you go back to that data and try and, with some kind of algorithm, detect the continuous periods of time when they were walking, so bouts of walking, and you analyze the complexity of those phrases, you'll find that those with higher complexity, I think it may have been lower complexity, I can't actually now remember which way it was, are more likely to develop cognitive impairment in the upcoming two years.
Yeah.
And so that's what I'm very keen to do. I started some of the work, and it's based on the fact the way we can be fairly confident that it's actually a walking balance is by looking at the posture. So that's why they need to be upright, otherwise they're clearly not walking. And then we combine that with not only the intensities of the walking, but we can also look at the frequency content of the signal. So we know that if a person is walking, they're going to take between 60 and 120 steps per minute. So therefore, we must have a fundamental frequency content between that range. Otherwise, it can't be walking. Because at the same time, we know that when people start jogging or running, their step rate goes up to between 150 and above. So that's how we can tell walking apart from running. There's other ways as well related to intensity, but I don't want to use the intensity measures because there's such a wide range of variability in the intensities we find when people are walking, depending on if they're in a really good condition or in a really bad condition. But step rates are going to be within that 60 to 120 range if you're walking.
Okay, let's get back to that in a moment and hear a few words from our sponsors.
This podcast is sponsored by Fibion, a research device that has been shown to be valid in tracking sitting, standing, physical activity and energy expenditure. Get scientific validation and learn more about Fibion at fibion.com/research. The Physical Activity Researcher podcast has created an activity tracker purchase guide for researchers. Get your free copy from the link in the podcast description.
And about the dual task, I was thinking could you actually somehow know from the data that they are having a dual task? I'm thinking if there would be, for example, a microphone or accelerometer that would detect that when they are, for example, talking, that you would actually know that now they are talking and walking, and then you could look like the changes in the walking variables.
Right. That'd be really, really interesting. At the moment, we're not there. In my case, I have no way of knowing whether it's why they're walking, because why they're walking is a really important question. In determining your walking velocity, in determining variability as well. So was there a second task they were undertaking or not? I don't have answers to these questions. What you suggested is something that a way of potentially doing it. I have actually heard of a study where people wore a camera medallion, which took a photo every 5 minutes?
Yeah.
So there are people have tried this. People have signed up as volunteers for these sorts of experiments, but I think from practical point of view, it's a little bit problematic to be recording someone's audio around a person 24/7 or taking a continuous stream of video. So some people might sign up for that. I personally would not sign up for that.
Yeah, I can easily see that. Yeah, I'm thinking also maybe having an accelerometer on the wrist. Maybe you could detect when the person is holding a phone.
Yeah.
So then you could know that now it's again a dual task. If so, I find it really interesting that actually when you just start to look like the data, you can detect so many things from really data streams that you wouldn't expect. That from a microphone you can get actually quite many things, and for example, Suunto is using the compass that when you actually swim and you make a turn, you can count laps in a swimming pool from the compass. It's of course. So it's just really, really interesting what you can get out of data when you look just deep enough.
Right, and there's so first of all we got different sensors. We got GPS, compass, or magnetometer, accelerometer, gyroscope. We could be measuring electrical activity like heart rate, muscle activity. And then, of course, there's the question of how many sensors are we wearing. So, like I mentioned, if you had one on your wrist, you can start figuring out and this has already been done. From a wristband device, you can, provided that it's always worn the same way, you can differentiate between having your arm flat. So now you're probably typing, you're doing some sort of, you're drawing, something akin to that. If it's pointing down, then you know that they're upright most likely, or they're sitting with their hands down for some reason. So that's one of the things you can do with just accelerometers. But if you make this inertial measurement unit, so inertial measurement unit has an accelerometer, but it also has a gyroscope, and it's very often also coupled with a magnetometer. And when you have these three different sensors in the same unit, you can then tell the orientation of the device to a very high degree of accuracy on any given point in time. So now you're starting to know the absolute orientation of, let's say, a segment of your body. And if you had one in each segment, so you had one in the forearm, another one on the upper arm, you could then compare the orientation of the segments, and you get the joint angle. And now, going back to, we don't really know what people are actually doing when we see a particular level of acceleration from the waist. If you, instead of having that, you had the posture of the body to, let's say, 10-degree precision of all of the joints in your body, you'd have really educated guesses as to what they're doing. So if you're pedaling, you'd see the legs pedaling away, so that's cycling, so it's either stationary or on the actual bicycle. Walking would be very easy to detect, running would be easy. So there's a lot of things you could start detecting. Dual tasking, that's a difficult one. But certainly, let's say you're walking hand in hand with someone, that would show up in the posture of your body, or if you're holding your phone to your ear, that would show. So potentially you'd get a little bit more insight.
Yeah.
I'm not entirely sure people are willing to sign up for that, or whether they're willing to sign up for that or not. That's one of the things I've pitched, or I've submitted as a grant application to the Academy of Finland in the past. They didn't see the value in it, unfortunately.
Yeah. No, it's been very interesting talks, and is there something, like, you have been doing research quite a long time, and you know, not everything fits into scientific publications, but you have probably learned quite many lessons doing research. Is there something you want to share, do's or don'ts for with other researchers? It can be small things with doing studies with accelerometers or with funding applications that you would like to share.
Well, I think there'd be a lot that I'd like to share, but I stick to my favorite topic, which is numerical analysis.
Yeah.
And one of the things, so this may be particular to sports science, but what I found is a lot of people don't actually do their numerical analysis themselves. And because they don't do numerical analysis, it seems like they think that numbers just fall from the sky, or this was done by pixies or fairies, which is of course not the case. There's always a human being who developed some sort of algorithm, and that algorithm can be really bad. And unfortunately, the more algorithms you take a look at, the more bad ones you find. And the one I just stumbled upon very recently was on wristband accelerometry. So from accelerometry, we typically are interested in energy consumption. And that's precisely what I was looking at. I was looking at the literature, going through the literature and trying to find equations or approaches to estimate energy consumption based on the accelerometer signal. I found a few relatively new ones. One of them was machine learning-based neural network algorithm, and they made it available to scientists, so you can pop your own data in it and you get energy consumption estimates. And they had three different options there. So one was for completely agnostic to the orientation of the device. That's the one I ended up using for a very good reason. But they also provided a version where it took a look at the three different dimensions independently. So it took a look at the x acceleration, y and z acceleration. And the assumption, the implicit assumption is that those axes are in the same order with respect to a wrist as they were in the dataset that was used to train the model. We actually used a different brand of accelerometers compared to the one that it was developed on, And this was immediately obvious to me that this is a caveat that might have implications. And of course, it turned out that the acceleration, the axes were different between our brand and the other brand.
Yeah.
And therefore, the energy estimates were completely different. So we were seeing like 6 times your basal energy consumption overnight when they were asleep. This was all caused by the axis.
Maybe people were happy with this feedback that they were doing enough vigorous activity.
I didn't provide this feedback, so I used the agnostic, and that's probably why they provided that direction agnostic version, because they realized it, but it's seldom spoken about. It wasn't obvious from the paper that you should never ever use their direction dependent version unless you have the same brand, or if the device you're using happens to have the same acceleration axis.
Yeah.
But that's by far not the only example. So while I was going through this, I also used a regression equation which was based on, it's called ENMO, E-N-M-O, so the Euclidean norm -1. And that's a... So in the past, what we had from accelerometers, we only got counts. So this was based on one company called the Actigraph. And they were the first to market with these physical activity measurement devices you could utilize without knowing how to do analysis. And they provided counts. So they provided, I think that it probably was for every second you got a count value. But the count doesn't actually mean anything. It's an arbitrary unit. Okay, so that's the history of it. Then other people flock to the market with products to measure accelerometry, but they can't produce the same counts the Actigraph produces because that's a proprietary algorithm. So it's not public how to produce counts, so you can't produce them. So therefore people thought, okay, we better come up with a way that's independent of which device you use to record your acceleration. And so people came up with this NMO value. And what it is we've got 3-dimensional acceleration. You measure a value of 1.1 on the x-axis, 0 on the y, 0 on the z. And you take the diagonal. So you square all of these values something together and take the square root, and that's your norm. That's a Euclidean norm. It's the same as magnitude. There's many names for it. That's what it is. And then you take 1 off from that value, and that's your NMO. This works if you've got perfectly calibrated devices, so they read 1G when they're stationary. But most devices don't read 1G when they're stationary, so they might read 1.1. And so that's what happened. And it's also axis specific. So while you're stationary, we always got the pull of gravity. And now if my z-axis is less sensitive than my x-axis, it means that my NMO value will be different when x-axis is up compared to z-axis is up. And so that's what happened with the wrist-worn accelerometers we were using. And it then resulted in 4 multiples of metabolic energy rate being indicated overnight when the people were asleep.
So it makes such a big difference.
It makes a huge difference because what we're looking at when we are accumulating acceleration. So first of all, what we do is we'll take, let's say 60 seconds of acceleration. For each recorded data point, we calculate the magnitude or the Euclidean norm. Then we take the mean of those values. If we got a static or like a DC component, direct current component that's offset by 0.1, in order to match that with a oscillating signal, which is what we normally have. So normally we have oscillation around the 1G when we're walking. In order to match a 0.1 value with oscillations, we need to actually have peaks that are like 2Gs and troughs that are close to 0G. And that requires vigorous walking. And hence, we get 4 minutes with a DC component that's actually quite small.
All right, so basically, quite many accelerometers are not calibrated correctly, or why do you get this wrong value?
That's precisely what it is. They're not calibrated. Some manufacturers are more explicit about not having calibrated them than others. So sometimes it's difficult to find out whether they've been calibrated or not, but it's very easy to test. Just pop it on the table, record for 5 seconds, and turn it at 90 degrees in a different orientation, and you'll find out whether it's calibrated or not.
All right, that's very interesting. have you published anything?
No. So you asked about unpublished findings.
Yeah, no, I think that's really important. Like, and this affects more to the count-based calculations, or
okay. Going back to what you can do to avoid this effect is instead of using the NMO value, you filter your data first. So you high-pass filter. High-pass filtering takes away the direct contact, so the constant component, and so therefore it's all zeros when it's stationary. So this is to my knowledge there are two proposed ways of doing or quantifying accelerations into like physical activity. So one is NMO and the other is mean amplitude deviation. And the mean amplitude deviation, the mean part there means that we take off the DC component first and then we look at the amplitude, the deviation from that mean. And so now any calibration inaccuracies are taken away by subtracting the mean.
All right, I would recommend publishing. Usually, this kind of method papers get quite a lot of.
So it's a known phenomenon. So this NMO problem has been pointed out by someone. I can't remember who it was.
All right, yeah. Probably not many people have read it.
And I think the bigger issue is not understood it. So even if you read it, you might not understand that this actually makes a big difference to what you're doing.
Yeah. All right. No, that's very interesting. Yeah. So we've been talking 1 hour. I think it's good time to wrap it up. It was a pleasure to talk with you. It was very, very interesting discussions. And maybe we have another episode of podcast when you have some results from your interesting study. So let's see. Thank you for being here.
Yeah, no worries. Thanks for that.
Yeah, thanks.
This podcast is sponsored by Fibion. Get scientific validation and learn more about Fibion at fibion.com/research. The Physical Activity Researcher podcast has created an activity tracker purchase guide for researchers. Get your free copy from the link in the podcast description.
Thank you for listening to the Physical Activity Researcher podcast.